Welcome back. This lecture is on function signatures, and I have a variety of functions here to show you and their signatures and what those signatures mean. So the first thing we're going to do is go in here to our solution and add a new solution folder, which we're going to call Module 2. In Module 2, we'll go ahead and create another console application. Make sure that we're in F#.NET Core, console app.NET Core. We'll give it an appropriate name here. We'll call it Module 2 Test Console. And throughout this module, we'll use this whenever we want to write some executing code to test. For now, what we're going to do is go in here and add a new folder to this project, which we'll call scripts. And then in scripts, we will add a new item, and we'll add a script file. And we'll call this function signatures. So we have our script file called function signatures. Now I'm going to copy paste some code in here into this script file, and then we'll go through it one line at a time. First thing that I put in the script file is open system. That's just opening the system namespace and the .NET framework, because there's some calls in here that use system. So I'm just going to start off by putting that into my F# interactive by holding the Alt and pressing the Enter key. You don't get anything back except the prompt returns. You see that down here. That just tells it opened the system namespace so that it can access those things. So let's look at the first function signature. We have here a very simple function, let add AB equal A plus B. Now, the compiler does what's called type inference. And so it has inferred from the fact that this is A plus B that the most likely candidate for these are int. So when it created the function signature, it created them all as ints. And you see here that this says that we've got an A coming in and a B coming in that are both integer parameters, and it's returning an int result. These arrows tell you what the parameters are, followed by, at the very end, the return value. These may be broken up a little bit differently, and I'll show you that shortly. Here we have a multiplication. Now I've done something a little different here in mul. I've decided that A and B are going to be float. Now if I just made these without these types in here, type inference would force them to be ints. There's other ways for these to become floats, but this is the explicit way. So A is of type float and B is of type float, and the result is A times B, and the signature is A, which is a float, B, which is a float, and it returns a float. That's its function signature. So let's put a couple of these into the interactive and see what happens. We'll put in add A plus B, and you see down here we get the function signature, and now we can type add 1, 2, double semicolons, and it returns a 3. We can do the same thing with mul. It tells you that mul takes a float and another float and returns a float. So let's type in mul 3.0, 4.0, double semicolon, and enter, and that's 12. And so that works. Now we've got a slightly different kind, and I'm going to talk about this in a little bit more detail here. I've created a function called log, log s, whatever s is what we want to log. Printfn takes this %a. %a basically prints any type, and it does the equivalent of calling toString on that type. Whatever that value is, it will print out according to its own specification. And so s is any type. And what we've got up here is a type signature that says log has a parameter s of type tick a. Tick a is a generic value. Whenever we put a tick at the beginning of it, it's going to be a generic. It can take on any type that's reasonable for it. We can also apply type constraints, though we'll be talking about type constraints in a later module. and it returns a unit. Now, unit is a special value, and we normally specify that as an output or an input with double parentheses side by side. It's a special symbol. We'll see that unit symbol in a moment. But unit basically means it doesn't return anything. So we can infer something from this, which is that this must do some kind of side effect. If it's not returning anything and it's a useful function, it must be going out and doing something. And in fact, it is. It's calling, in this case, printfn, which prints to the screen. So if we run that into the F# interactive, you see down here, S is of type tick A or any type, and it returns a unit. So if we go log my name, double semicolon, it printed, you can see here, it printed my name, but it printed it as like a toString, and so it printed it as a string. We could do this slightly differently, and I'll change it slightly here. We'll make it a %s, and we'll see what it comes up with now. Now it says it's a string. Before, it said that the type was a generic, but this time it said it was a string. That's because the type inference system has the ability to understand these format identifiers, which is really handy because it'll also tell you if you've made an error. For instance, if I put a 3 here, it comes up with an error. It says that the expression was expecting a string, but it got an int. So we'll put S back. This log function now takes a string, so I can't say log 3. I'll get an error, which I did. But I can say log Bill. Oops, I got to put double semicolons. Always remember that. Now, notice something else here. It didn't put quotes around it. Earlier, when we did my name, it put quotes around it. That was because of the format identifier of a capital A, which it was really printing out the type along with its value. It was saying it, putting it in quotes, saying it's a string. So it was printing out its format according to its print string, which puts quotes around it. Or it's not print string, but toString function, or the equivalent thereof. In this case, because it knows it's a string already, it just printed Bill on the screen. And it returned a type signature when we ran it in there of returning a unit still. So it still returns a unit. It doesn't return any value. It just prints out to the screen. So let's take a look at this next one. This next one, random alphanumeric string, takes a unit. So we don't give it any parameters, but it returns a string. So we can infer something by that. This is making up a string. It's making it up in some way, so it must be some kind of a side effect. It must be relying upon something. In this case, it's relying upon a random number, a random number generator from the .NET framework. And it's this random call here, random object here that we needed the system, open system for. So let's put this one in. And you see that we get a value. Random alphanumeric string takes a unit and returns a string. And if we go type in random, I'm going to copy that, paste it on here, and we put these two this symbol after it. This means I'm not sending any parameters, but I am calling a function. And we put double semicolons, and we get a random string. If we run that several times, we get a different string. Now, what did I say about functions? For the same input, they cannot put out different values, and this one does. So this one also is not a function, and neither is this log. Log is not a function, but it's useful. It's got a purpose. It serves a purpose. In the case of here, it produces a random string, and we'll actually use this for a couple of capabilities. We'll use it when we start working with passwords and analyzing them. We will use this to generate salts in order to hash a password, and we're going to use a similar function to generate random passwords. So here's a slightly different one. This one, called max, takes a list of int. The value is called list. It's on the left of this colon, but it's an int list, and list here is a special keyword. Well, it's not a keyword. It's a member of the list module that tells it that I want a list of integers. It's a very compact syntax compared to doing that in C#, which we would have to say list of type int equals something. And we would have to new it up and so forth. This just says we've got an int list. And what it's doing here, we'll talk about this pipe symbol eventually, but basically this takes this list and puts it over here as a parameter to max, and it makes for a little bit cleaner syntax. It says we're taking our list and piping it to list.max. Let's take a look at that one. Alt enter. Where'd it go? Max. Oh. Let's do that again. I'm not sure it went in correctly. Yeah, there it is. It takes an int list and it returns an int. If I now go, darn it, max, and a shortcut way of making a list is in square brackets, putting your list with semicolons separating the elements of the list, and that should be 7. I've got to put double semicolon, and it is in fact 7. It found the maximum number within that list. List.max is a built-in function inside the list module. So this list with a capital L is not an object. We'll get into modules eventually. I'm not really here talking about lists. I'm really talking about type signatures. So you can see that it takes a list, which is what we send in. We send in a list, and it returns an int, and it did. It returned an int that was the maximum value. And the last kind of function that we're going to talk about is a curried function. And their signature looks a little bit different. We're going to talk about function currying in other modules, but for now, just understand and recognize this signature. This is saying that we're taking an int and we're returning a function that takes a unit and returns an int. And in this case, it's kind of silly and simple, but this function, curried function A, simply returns this function here, and then this function here just adds 1 to that function. And of course, this is where this inner function is where it returns that inner function of it. So let's put it into the interactive. Oops. Let's put it into the interactive and see what happens here. Copy all this, put it in. So curried function takes an int and returns a function that takes a unit and returns an int. And let's try that out. Let's say curried function 3. The answer to this should be 4. It returned a function. I forgot to put the unit after it. Now we get a 4. Okay, my mistake. That's because of the way I designed this. There's another way of doing this that would make that a little bit easier. But yes, we do have to put the unit after it. And if we put that in now, we get 4. You'll notice this is actually correct. It actually, when I put that 3 in, it returned the curried function, unit int. And here's the function, the curried function that it returned. But if I want to call that function, I put the unit after it because it takes a unit. And there it is. It added 4. It ran that inner function. We could also do something like this. Let add 1 equal curried function 3. We run that in, and add 1 is now a unit that takes an int. So we just go add 1, put the unit marker after it, and we will always get a 4 out of that. We can't ever get anything else out of it because we put the 3 in up here, and that's partial application. We'll get to partial application in another module. So that is it for this section on function signatures. We'll be talking in a lot more detail about these functions and types and everything else we can do with this. Systems like this function right here, we'll go into detail on those. We're actually going to be building some functions very similar to this as part of our final application. So Thanks for watching, and I look forward to seeing you in the next lecture.